Our next speaker is Russell J. Hendel, who will talk on a system of 4 simultaneous recursions. Please, go ahead.
Thank you. Is the recording on? Because I can't see it on my screen, but that's okay. What? Mel, is the recording on?
It is on.
Good. Okay. Well, first, I thank the organizers for this is my second conference, not my 10th, but I've been enjoying myself so far. And I thank those who have stayed late to listen. So let me go over some things on the title slide. I didn't know how to title this. On the one hand, Leiden in the 60s of the last century noticed some interesting patterns in Fibonacci numbers, which we'll get to later. Shannon and Ollerton, in a paper last year in the Fibonacci Quarterly, said, well, we can prove the case completely by reducing it to known sequences in OAIS. I looked at that, and so that's the Leiden part, the Shannon and Ollerton part. I found a more direct proof, and I generalized it further. So that's the content of the talk, and that's the second line of the title. But I began thinking, why did I get away with this when no one else did? And I have a method here that may be of interest. Very often with identity, sometimes the identity is interesting, sometimes the method is interesting. The identity requires 2 polynomials, but and I spent about a month till I realized this, when I use 4 polynomial families, everything becomes very, very elegantly stated and proven. So the first line deals with the method, the second line deals with the content. Okay. So I'm going to have 4 parts to the talk, not very elaborate. I'm going to go over what Leiden, Shannon, Ollerton, and my generalization is. Just look at examples. Then I'll state the main theorem. I'll state it in 2 ways. I'll state it at a high level, saying that something exists, and I'll tell you what the thing that exists is. I'll mention the contributions of this paper over the previous works, and I'll go through the proof, which, as I said, becomes very elegant when done this way and very straightforward. Okay, if you look at the top line, you're summing k squared times fk from k equal 1 to n. I assume everyone knows the Fibonacci numbers. It's an undergraduate topic, but if you don't, f0 is 0, f1 is 1, and f of n is the sum of the previous 2. So this is looking at a sum of basically polynomials or squares times Fibonacci numbers, and that's a function of n, p, and m. P is the power, it's k squared. M has to do with the Fibonacci recursion. And what Leiden noticed for a few cases is that there's a closed form for this sum. This is the identity here, n squared minus 2n plus 5 times fn plus n squared minus 4n plus 8 times fn plus 1 minus 8. And you can check that by looking at various n. And as I said, Leiden noticed this for a few p. Shannon and Ollerton generalized it for all p. So I said, why not go a step further? And this is my generalization. Here, the pk are the Pell numbers. So p0 is 0, p1 is 1, and p of n, instead of being pn minus 1 and pn minus 2, is 2 times pn minus 1 plus pn minus 2. So the multiplier of n minus 1 is 2, and that's the m here. Power is 3. Again, we have a sum of powers times recursive sequence. And again, you have, just as in the top line, you have a polynomial in n times pn, plus another polynomial in n times pn plus 1, plus a constant. So that's what you see here. And what I want to do is generalize this to all cases, all p, all m, and I want to get a nice proof. But these are the examples that motivated this. So let us go on to the main theorem. First of all, I have to tell you formally what the metallic sequences are. G0 is 0, G1 is 1, and Gn is m times Gn minus 1 plus Gn minus 2. The reason they're called the metallic sequences, and that's certainly not the only name, you can call them the shared Fibonacci sequence or other names. When m is 1, you get the Fibonacci sequence, and the ratio of 2 Fibonacci numbers approaches the golden number. Well, gold's a metal. When m is 2, you get the Pell numbers, and some people call the ratio of 2 consecutive Pell numbers the silver sequence, silver constant. So the idea is the metallic sequence, and it occurs in certain literature, it's not certainly standard or non-standard. You can get bronze and copper and various other types of sequences, but you don't have to be fancy. I'm dealing with this set of sequences. And the initial conditions are important. And as I said, we just have a multiplier of J minus 1 by M. I could put in another multiplier here, but I have not. And I found the generalization of the for the Pell number so easily. I said, well, it's just a piece of cake to get it for all of them. And it took me about a month because there are some obstacles. The target function is again a function of N, P, and M. You're taking powers of K, 0 through N. You're looking at the metallic sequence. So when M is 1, this is Fibonacci. When M is 2, it's Pell. And you're summing them through N. And the theorem you want to state is for each M and P, there exist polynomials Fn and Tn, which of course depend upon M and P, with Sn MP equal Fn Gn plus Tn Gn plus 1 minus T0. And there are a lot of symbols here. So F stands for the first polynomial, T2 stands for the second one, or the number 2 polynomial. They're just two polynomials here. And if you go back here, I'll just show you again. That's what these two examples look like. You have a polynomial times Fn plus a polynomial times Fn plus 1, or times Pn and Pn plus 1. Okay, that's a high level statement. I haven't told you what Fn and Tn are. I just told you they exist. So who are Fn and Tn? Well, I'll need 4 recursive polynomial families. Actually, I should only need 2, but I need 4, which makes the proof nicer. This looks a little bit intimidating, but it isn't. So let's see if I can go through this. F0x is 1. That's pretty non-intimidating. If you have an Fix, then Tix is a sum of binomial coefficients times shifts of the Fj. D stands for difference, is the difference of Ti and x times Fi. Sis stands for sum, is the sum of Fi and Di. And then Fi is again a sum of binomial coefficients times shifted amounts of the S function. And as I said, when I was doing this, it took me about a month because I was only looking at Fi and Ti, and you can do the whole proof without it, but there's a lot of computations and a lot of tedious algebra. And finally, one day I realized if I had 4 families, everything would look much simpler and much more elegant. So these are the 4 functions. And then I can tell you what the, I'll just go here. Fn is this. You take the Fi, which I just defined, divided by M. Well, you have, it's a polynomial here, and Tn is that. And you can plug these in and you can verify that this works for the case I showed you at the beginning, K equals 2 and M is 1. It works for K equals 3 and M equals 2, and it works for anything. This is exactly what we want. I'll just mention here that these polynomials give rise to new OEI sequences. I haven't put them up yet, but they are new. So let's just look at this. F0 is 1. That's a polynomial. What's F1x? F1x is 2 minus x. So you see here the 2 minus x. F upper 2 of x is 8 minus 4x plus x squared. F3 of x is 48 minus 24x plus 8x squared minus x cubed. And you get this triangle here, the coefficients of the powers in ascending order. And it has many interesting properties. There are properties on the diagonal and getting a little bit jumpy here, properties on the diagonal and on the columns. So if you look at this diagonal, you see 1 minus 1, 1 minus 1, 1 minus 1. If you look at the second diagonal, 2 minus 4, 8 minus 16, that's just powers of 2 with an alternating negative sign. I'll just mention one more. If you look at 1, 2, 8, 48, etc., you have I factorial times 2 to the I. For example, 48 is 2 cubed times 3 factorial. 8 times 6 is 48. 384, for the case of 4, is 4 factorial, 24 times 2 to the 4 times 16. And if you multiply 24 by 16, you get 384. So there are patterns here, and there are interesting properties. And of course, we already define the polynomials, but the coefficients themselves have interesting properties. And there are other triangles for the T, for the D, and the S. Okay. Okay, so I've shown you the examples and shown you the generalization. I just want to state what I've done that Leiden and Shannon Overton did not yet do. First of all, I'm generalizing it to all the metallic sequences. Shannon and Overton at most went to the Fibonacci numbers. I'm going to all of them. The key idea, as far as I'm concerned, is the method, and I'll mention some of the methods of Shannon-Overton in a second. I use 4 polynomial families to define 2 polynomial families. And by having those extra 2, the proofs come out very elegantly and everything else. So I consider that a major contribution. The other contribution I make, and we'll see this later, is at various points I have to prove that 2 functions are equal. The functions are polynomials, but they have different arguments. So I use the shift operator to make sure the arguments are the same, and then I'm proving polynomial equality. You prove polynomial equality by equating coefficients, not the same way you look at function equality. Finally, I'll mention that the Shannon-Overton paper, it was a straightforward induction. They did a lot of reduction to known OEIS sequences. In fact, Shannon-Overton said their contribution to lead-in is to utilize the encyclopedia of integer sequences to completely describe the case with Fibonacci numbers. I honestly couldn't see if the proof was complete or not. There are lots of conjectures. Their proof itself, there was a certain induction with lots of technicalities, and they ended up reducing it to properties of the Bernoulli numbers. I've bypassed the Bernoulli numbers. My proof is self-contained. And I was hoping, since I have a self-contained proof and I proved the same thing they did, I could prove some of their conjectures, some of the statements they made about Bernoulli numbers are interesting. But anyway, this is what we're doing. We're doing for all the metallic sequences, introducing a new method, and it's self-contained. Okay, let's go to the proof. And I again emphasize, because we define 4 polynomial families, proof is line by line and easy to follow. So let's assume M and P fixed. I'm going to write Sn instead of SMMP. The proofs by induction, the base case n equals 0 is very clear. Well, here's what I have to prove. And let's see, Sn is a sum from 0 to n. Well, if you're summing from 0 to 0, you're going to get 0. Okay. I have F0, G0. G0 is always 0, so this term is going to get knocked off. G1 is always 1. And when n is 0, I get the constant term of the t polynomial, t sub 0. So I have t0 times 1 minus t0. That's t0 minus t0. That becomes 0. So I've just proven the base case. And in case you're curious, again, more notation. If I have a polynomial b of x, I will write that of degree d. I'll write that as the sum I equals 0 to d of bi x to the I. So I just use this convenient subscript notation to indicate the coefficients of the polynomials. So T0 is indeed the coefficient of x to the 0, or the constant term. Okay. So the base case is usually quite straightforward, so we won't dwell on it anymore. We now assume it's true for the case n. In other words, we assume that equation true. We need to prove it for the case n plus 1. We need to prove that Sn plus 1 is Fn plus 1 Gn plus 1 plus Tn plus 1 Gn plus 2 minus T naught. Well, how do we do that? By the induction assumption, Sn plus 1 is also Sn plus 1 more summon, n plus 1 to the p, Gn plus 1. Remember, Sn is just a sum of powers times elements of the sequence. So Sn plus 1 is just what I had before, Sn and this. I know what Sn is, it's this. So I'm going to plug this top line into here, and I'm going to get that Sn plus 1 is all of this. Now, I'd like to compare these two lines. They're both Sn plus 1, but here I have Gn plus 1 and Gn plus 2. Here I have Gn and Gn plus 1. That's not a problem because the recursion tells me that Gn plus 1, and Gn plus 2 are related. So I can write Gn in terms of Gn plus 2 and Gn plus 1, and that allows me to write the second equation. So I'm going to obtain an equivalent to prove by writing Gn as Gn plus 2 minus Gn plus 1, which is just defining recursion. Gn plus 2 is mGn plus 1 plus Gn. I'm going to plug that into here for Gn, and I'm going to get another statement of Sn plus 1, which is this. Sn plus 1 is the Tn Gn plus 1, but I now subtract mFn Gn plus 1, and then I'll have the Fn Gn plus 2 minus T naught. I'll have an m plus 1p to the Gn plus 1. And the nice thing here, and this looks very simple, but this is what makes the proof go, I define Tn minus mFn as Dn. Remember, that's the difference function, the difference of T and a shift of the F function. And it's these extra two families which makes the proof so much easier. At this point, I've said, if I assume Sn is true, if I assume the induction assumption, I need to prove for the case Sn plus 1, I have one start equation here, one start equation here. So to prove the induction step, all I have to do is show that these two are the same. And the left side of the last two start equations are the same. They're both Sn plus 1. Therefore, the right sides must be the same. So I have these two must be equal. And if I can prove that, I've proven the case of Sn plus 1 from Sn, which is what I want to do and completes the proof. So I'm going to copy that in the next slide and show you the problem we are stuck. I want to prove these two are equal. Well, the natural thing to do is say Gn plus 1, Gs plus 1 equate coefficients. Gn plus 2, Gn plus 2 equate coefficients. So you want to write that these two functions are equal. Now, they are equal, but proving functions are equal is not trivial. So we get stuck here, and they are polynomials with different arguments, and proving polynomial equality is easier than proving function equality. So I want to make this start equation into an equation where the dn and the fn have the same argument of n plus 1. So I need a little shift operator, and I'll do it by example. I think that's easiest. Suppose Rx is x squared. It's a polynomial. Now let's look at the polynomial Sx is x squared minus 2x plus 1. So I hope it's obvious that Sx plus 1 equal Rx. Let's see what that means. That's x plus 1 squared minus 2x plus 1, which is the square of x plus 1 minus 1, or just x squared. So Sx plus 1 equals Rx. Well, that's what I want. I'm going to define a polynomial R bar, x plus 1, to equal Sx plus 1, and then R bar x plus 1 equals Rx. And such a polynomial will always exist that allows me to replace the dn by d bar n plus 1 and the fn by fn plus 1. So the proof is completed by proving that this fn plus 1 is d bar n plus 1 plus n plus 1p, and tn plus 1 is f bar n plus 1. Why is this so nice? Because I don't care about the n plus 1 or the n or anything else. I'm just going to prove polynomial equality of these two polynomial equations. Polynomial equality simply means look at all the coefficients and show them the same. And that is now very straightforward. So this is the end of the proof. The coefficients of, so let's look at this. I have to deal with t, f bar, f, and d bar. The coefficients of ft defined by the system of 4 polynomial families. So let's see if I can go back here and just show that to you. I'm not going to go through the details. It's a little bit hard when you're doing slides. Fn and Tn are defined in terms of Fi and Ti. There are some binomial coefficients and oscillating signs, but that is the coefficient of Fn. Here's the coefficient right here. That's the coefficient of Tn. And the Fn and Tn I've defined here. So I can write down a closed formula, and it's a double sum with some very nice binomial coefficients. And I can write down explicitly what the coefficient of Fn and Tn are. I can also write the coefficients of R bar from R using the idea above that Rx is Rx plus 1 minus 1, because x plus 1 minus 1 is x. Then I'll just show this to you again. If I want to know what R bar is, I just write this as I do that by expanding x plus 1 squared minus 1. I get x plus 1 squared minus 2x plus 1, and that is R bar x plus 1. So you can write that down in a closed matrix form, and you get some closed formulas for R bar x. The point is they are closed, and they tell you exactly what the coefficients are. So I know the coefficients of f and t. I know the coefficients of R bar. I simply have to verify the equality of coefficients of polynomial, and that completes the proof, because all I have to show is that f equals d bar plus n plus 1 to p, and t equals f bar. And I didn't do this in the presentation because there's some of these double sums, and at the end there popped out a an identity in binomial coefficients, which I'd never seen before, but which is true. The details of this, there is an archive paper if you want to read it, but you could sit down now and do this yourself. So you get a line-by-line proof, very straightforward, and that completely proves this. And with that, I just want to thank you for everything, for listening. I'll take any questions if there are any.
Thank you, Russell. Are there any questions for our speaker? If not, then Russell, I thank you again. And our next talk is in 10 minutes.